There's a funny thing about Kepler. Kepler had been designed to find planets, but lo and behold, it always seems to happen. You build the perfect machine to do one thing, and all of a sudden you discover it can do something else. And those are those fortuitous discoveries that change science in ways that nobody had expected. Now, our speaker tonight, Soren Meibom, he's done something different with Kepler that resulted in a big news conference for us last January. And when I saw what he had discovered and what he had done and how it changes our search for life in the universe, I said, you've got to speak to our crowd and share with them what you've come across. So, while he's getting set up and feeling comfortable, you ready? Let's find out a couple other things that Kepler can do.
I'm very excited to be here for several reasons. One of them is that I cannot tell you how many times I've come in on a Thursday night for a Friday deadline and have absolutely no place to park my car. But tonight, I have no deadline and I have a parking spot. So this is starting off well. What I'm here to talk to you about is, you know, when all of us step outside on a dark, clear night, we can't help ourselves but look up at the sky and look at all this beautiful view of all these stars. And the longer we look, the more we see. And our children will do that, and their children. Our parents and grandparents did that, and countless generations before them all looked up at this beautiful night sky. And they all wondered about what it was. And they asked these questions about them. They, like, what are they, right? And, let's see, how far away are they? What are they made of? And what makes them shine? And we happen to be, amazingly enough, living at a time and in a generation where we actually have a substantial understanding of how stars work, how they form and live and die. And we can answer most of these questions now for most stars. Now, considering that, it's somewhat surprising, at least it was for me when I started studying astronomy, that just like it is the case for most stars of the TV screens and the movie screens, one of the questions that causes us the most trouble is the question of how old are they? Okay? And so, of course, that's what I'm here to talk to you about tonight. And as you'll see, even without the complications of plastic surgery, that question is hard enough to answer. It should be on. Can everybody hear me? Okay. So, let's get started. Let's start by reminding ourselves of what is a star and how does it form. It all starts with a big cloud of gas and dust, and it becomes unstable and it starts contracting, collapses onto itself. And in the center of it all, you form this sphere of gas and matter keeps falling onto it, and its energy is released in forms of heat. And eventually you form this protostar in the center. And what happens is that in the core of this protostar, eventually it gets so hot and so dense that it reaches these incredible temperatures where the process of thermonuclear fusion makes hydrogen fuse into helium, which eventually, as a byproduct, produces a lot of new energy that in form of light is emitted in form of light. And so the core of the star lights up, and eventually the light diffuses out through the rest of the star, and the star is born. So that's the process sort of in a nutshell. Now, our sun started like that. And it goes through an amazing 620 million tons of hydrogen every second. Right? Think about it. Now, that also happens to be as big of a number as it is. It's a very, very tiny fraction of the mass of the sun. which means that they can go for a long time. And it has been going for about 5 billion years, right? And it will go for another 4 or 5 billion years because this is a small amount of its mass. Now, in this animation down here that I showed you, you probably noticed that a few planets were forming as well around this star. And so this is a good point to sort of make the distinction between a star and a planet. Because the planets form as well out of this cloud of dust and gas, out of the leftovers, so to say. But they never become big enough or hot enough in their cores that the fusion can begin. And so the planets do not shine, right? They only reflect the light of the stars, just like in our own solar system. Stars come in many different sizes. There's a whole variety of them. In this figure, this is where we have the sun. The sun is a relatively modest star. It's a small star. And we have them, very tiny ones, about a tenth of this size and a tenth of the mass of the sun. Half as hot and only a 1,000 time as bright, 1,000 times fainter than the sun. We call those M stars. And all the way up to huge stars, we call them O stars, that are 7 times as hot, right? 20 times as big and 40 times as massive and 500 times as bright, 500,000 times as bright as the sun. So you can see there's a huge range. And these differences reflect themselves in how long these stars live. These small M stars, they live more than 100 times as long as our own sun. Whereas these big guys over here, the O stars, their lifetimes are 10,000 times shorter than our sun. The reason for that is that these stars go through their fuel, the hydrogen fuel they have in their cores, at very different rates. The little guys over here are like smart cars, right? Very economic. They drive forever. You put a gallon of gas in them. And so they use very little and very efficiently of their hydrogen in their cores. And so they live very long. Whereas the guys over here, like limo Humvees, right? They just like drive a mile in a gallon. And so they go through their fuel very quickly, and they come to the end of their tank or of their life very quickly. Whereas a good old sun is like, the car you want, right? If you just want to go 4.6 billion miles, all right? So that's the good old Corolla we have there. Now, for today, I'm going to focus on these small stars. And for these reasons, there are many more of them. Star formation operates such that you form many more of the smaller stars than you do of the big stars. So there are many more of them. And because they live forever, they represent all the epochs, all the times of star formation in our universe. If they form, they're still there because they live so long. And they also dominate in our solar neighborhood. So many of the stars that are close to us that we like to study in detail are amongst these low-mass stars. And they're also the ones that, as you've just heard, we start to find planets around. And we'll get back to that. So, why is it important to know their ages? Well, there's no way with the time available today that I can go in and touch on all the fields of astrophysics that would benefit from knowing having better ages of stars. Even if I had a lot of time, I myself couldn't think of all the specific studies, projects that will benefit from that. So instead, what I'll do is sort of make a general argument for why knowing the ages of stars are important, and then I'll give you a few specific examples. This text says in relatively few words that the reason it is important to know the ages of stars is that the ages are fundamental to understanding the time evolution. That is to say, how stars change with time. The time evolution of a wide variety of astrophysical phenomena, that involves stars and their companions. And so, to make that more down to earth, let me try an analogy. Let's say that you were an alien space pilot, and you're out there and you have a commander who tells you, go to this planet Earth and find out how these humans that we don't know anything about, how they evolve, how they change through their life as time goes by. But of course, it's a big universe, so if you're an alien space pilot, you have a very tight schedule. And so you only have about a few hours, okay? You go down here a few hours and study these humans. So you land your spaceship in, say, Cambridge Common on a Saturday morning, okay? And strangely, no one notices. You step out and walk down the stairs and you start looking around. And you see all these supposedly humans. And you see some small ones that are very fast. They run like crazy and they're very loud. And they know tons of tricks and have a tremendous amount of energy. And then you see some much bigger ones who seemingly are chasing the small ones, and but are not nearly as fast. And they have, started to develop gray hairs and stuff. And then once in a while, another human comes by, and all of their hair is gray. They move much slower, and they're very quiet. So based on that, these are your observations. You could see how it might be a reasonable hypothesis to say, well, clearly, these small, energetic, capable, fast, loud ones must be the end of the evolution. These are really cool, right? Whereas the other guys, the big guys, they have a ways to go. They can't even, keep up with them. And that will, of course, be wrong, because you didn't know the ages of these humans. And so that analogy was just to tell you that the same when we look out into the universe. We look at all these stars in all these different phases of their evolution. But if we cannot take them and put them on a timeline, order them chronologically, we might make the wrong hypothesis. We might get the wrong understanding of how they work and how they evolve with time. So, but I want to make a couple of things clear here. Is that even if we cannot determine the absolute true age of a star, okay, if we can't determine that it's 3.7865 billion years old, that's okay, as long as we can order them chronologically, so we have an order, or if we can come up with a time scale, like the differences in their ages. And let me show you what I mean here with a couple of examples. Let's say you've been out observing, and you have observed 3 different but similar stars. Okay, star A, B, and C. And you're a beginner, so what you have been able to do at this point is you've been able to find out that star A spins around fast. You don't know how fast, but it spins around fast. Star B spins very slowly, as you can see. And star C spins moderately fast. Now, when you think about that, you think, what does that mean? And again, until you can figure out which one of these stars is the youngest, which one is in between, and which one is the oldest, you have no real way of making sense of your observation. But if you can, and you do find out that star A is the youngest, star C is in between, and star B is the oldest, so you can see that the youngest spins fast, the middle-aged one spins moderately, and the oldest star spins slowly, then all of a sudden, you have a hypothesis, right? You can say that, oh, these yellow stars seem to decrease their spin rate with time. Again, you don't know the exact ages of these stars, but you know their order, the chronological order of their ages. And so you're able to actually make sense of your observations. Now, it would be even better if you had a way of telling how much older star C was than star A. Say that you find out it's 1 billion years older. And say you found out star B is yet 3 billion years older than star C. In that case, you see, you can find out how much the spin rate of a star in this case changes with time. Not just that it changes, not just that the stars spin slower as they get older, but how quickly they spin down. And the same, of course, for the other timers. So all that just to say that even if we cannot determine the absolutely true ages of the stars, if we can order them chronologically or determine their relative differences in age, we have ways of making sense of what we see, of trying to understand the astrophysics of the problem. Now, let me give you a few specific examples of why it's important to know ages. Let's think about the formation and evolution of galaxies like the Milky Way. Our galaxy has more than 200 billion stars, right? And other galaxies have even more. If we want to try to understand how these galaxies form and change with time, we need to be able to answer basic questions such as how old, which stars are old and which stars are young, to put the puzzle together of how these galaxies formed. Another example is the formation of planets and planetary systems. As you saw in this first animation I showed you, planets form around stars at the same time. And so planets and stars share the same age. And so if we can determine the age of a star, we can also determine the age of its planets. Now, you heard about this already. In 2009, the Kepler spacecraft launched. And Kepler, together with the HARPS project and many other ground-based surveys, have produced a fantastic zoo of new planets and planetary systems. And in that zoo, there are all these wonderful surprises. Okay? This animation just shows you those of the Kepler systems been found where there's more than one planet revolving around the star. And it's amazing. None of them we would have predicted would exist 15 to 20 years ago. They're all strange and wacky and completely, surprising to us. And that is, of course, wonderful. It has completely turned on its head our whole concept of planet formation. Okay? And we have to struggle with that. And just to show you one example in an animation here is this system, 6 planets, okay, are packed within a distance from the star that is less than the distance to Mercury in our own solar system. Okay? This is what we have to try to understand and explain when we're thinking about planet formation. And so, when we're looking at this picture, and we need to try to understand that, we need to make sense of it, one of the main questions that come to mind is, well, how old is this one? How old is that one? Which ones are young? Which ones are old? Which ones have just started their evolution? And which ones are at the end and have had 10 billion years to interact and to evolve? And so again, knowing the ages of the stars will give you the ages of the planets and the planetary systems. Okay? And so that will help you, even just with the chronological order. Now, what about the evolution of life beyond our solar system? This is a star. One of our ultimate goals right now in astrophysics, as you heard in the introduction, is to find these small, rocky, Earth-like planets in the right distances from their stars so that life as we know it could potentially exist on them. And when we do, and you can hear we're getting very close, one of the first questions we're going to ask ourselves is, how old is this star? And how old is the planet? Because we know from studying our own planet, the Earth, right, that when it was 1 billion years old, only the most primitive microbial life existed on it. When it was 3 billion years old, only slightly more complex life existed. Certainly nothing that a program like SETI on another planet would pick up on, right? These algae are not going to radio broadcast anything, right? And then only, right, 1.6 billion years later, we have a planet teeming with what at least we would consider intelligent life, right? And beyond that, in the future, who knows what's going to happen? Who knows how long it's going to last? So you can see clearly the question of age is essential to the question of the evolution of biological life. Now, the challenges of determining the ages of stars. Unfortunately, they don't come with the age tag. So, what we're faced with is the reality that we cannot directly measure the age of a star. Right? Think about it. We can measure other things of a star. We can measure its mass, its chemical composition, its brightness, and its size, and its rotation speed. But all of these things changes in the dimension of time. But time is not the real agent of the change. Time is not a force. Age is not a force. It's not a physical process. It's just the dimension that things change in. So we cannot directly measure the age of a star. Instead, what we must do is to try to get the best possible understanding of how stars work. We have to try and understand the physics of how stars work and collect all this knowledge into what we call a model, right? So we have a model for stellar evolution. And we can then use that model and compare it to our observations to give us an age of a star. Or we can say, well, we might not understand exactly why this property of a star changes as it does. But what we can do is we can try and observe this property for stars for which we know the ages and create a relationship between that property and age. We call that an observed relationship or an empirical relationship. And I'll lay out what I mean. So here you have the model scenario, the way you determine an age of a star based on a model. You have your model up here, and you see how in the model we have some prescription for how a star changes as time goes by. Okay, in this case, the star got bigger and brighter and cooler. Then you go out and you make your observation. And you look at your star and you say, oh, it's this big, it's this hot, and it's this bright. And then let me go back to my model and see when the stars have these properties, what does my model tell me is the age of that star? You see that process? When you have a model, you can use that. Of course, as many of you are sitting there thinking, this only gives you an age that is as good as your model. If the model is wrong, you'll get the wrong age. Now, today we have a very sophisticated and pretty good idea about how stars evolve, most of them at least. So the ages we get out are pretty good, but we have to keep in mind that the ages we get out are only as good as the model. The other approach we had, let's get back to our 3 stars that we observed. Let's say we've been hard at work and we figured out that we can do a little better than just finding out that they spin fast and slowly and moderately slow. We graduated, from our masters, and we have actually learned how we can measure the time it takes a star to spin around once. Okay? We call that the spin period of a star. And we find out that star A spins with 5 days, star B with 20 days. That was the slow one, right? The moderate one with 10 days. Let's also assume that for these 3 stars, one of our colleagues have actually found out their ages of them. And I'll get back to this later in the talk. So now we have these 3 stars for which we not only know the spin periods, the time it takes the star to spin around once, but we also have the ages. And we can take out our graph paper and we can draw an axis down here, a line with the ages of the stars, and we can draw another axis with the spin periods. And we can put our 3 stars on there, right? We have the half a billion year star, 5 days. The 2 billion year was about 10 days. And the 4 billion year old star was spinning with 20 days. And so now we are laying the foundation for creating this observed relationship between how old a star is and how fast it's spinning. This empirical, this observed relationship, right? And the idea behind that is that once you have that, even if you don't completely understand the physics behind why the stars are spinning down, you have measured how fast they do it. And if you can do that well enough, now you can go out and you can measure the spin rates of other stars. And you don't need to know their ages. If you can just measure the spin rates, you can use this relationship that you have established to get their ages. So you see how that's an alternative, different approach. Now, for both the model-dependent and the empirical, the observed relationship methods, still to this day, they both approaches are highly dependent on tweaking themselves to match the results we have for exactly one star. And you have already guessed what that is. That is the sun. The sun is the only star for which we have a precise and accurate and independent measure of its age. And it's not because the sun is particularly friendly to us. In fact, it's just as particular about its age as all the other stars. The reason for it is that occasionally some piece of space rock will fall down on Earth. This very cool picture was taken from the International Space Station just last month. And it shows what many of us have seen laying on our backs in a cornfield somewhere at some point, a shooting star, right? A shooting star is a piece of material, a piece of rock that is burning up in the Earth's atmosphere. This time it's seen from space, so I thought I was going to show because it's very cool. Zoom in, if it will. Here we go. Now, most shooting stars, they just burn up, so nothing comes down, but eventually and occasionally, these pieces of material are big enough that they don't completely burn up in the atmosphere, and they actually land on the ground. And most of them are either from dust from comets and small particles, or they're larger pieces from the asteroid belt between Mars and Jupiter. And they can look like this, either made of metal or rock. And sometimes they make very spectacular, if they're big enough, craters and impact craters on Earth. This is the Meteor Crater, right, in Arizona. And sometimes they make, less fortunate and less spectacular impact craters, like this one who hit the roof of a house. But the important thing is, this is actually material. Unlike all the other stars in our solar system, this is material we can pick up from the ground, go to the lab, and measure through the decay of radionuclides. We can measure how old these are. And since they're from the very early solar system, formation of the solar system, we use that as a constraint on how old the sun is. And so the sun is 4.567, and I could keep going with the digits. It's very precise, billion years old. Now, let me give you another example then, or not another, let me give you an example of how you can use these models of stellar evolution to determine the ages of stars. There's a very important, very valuable category of astronomical objects called star clusters. Star clusters are families of stars, in the thousands of stars, that are all born together at the same time out of the same cloud of dust and gas, out of the same material. So they share the same age. All the stars have the same age. They have the same chemical composition because they're made out of the same material. They have the same distance to us. And these are very important properties. But they're still a family, so they have their differences. And the differences are in the sizes. In a star cluster, you can have thousands and thousands of stars, and they all have different sizes. Okay? And as I told you early on, depending on the size of the star, it goes through its life in a very different manner, right? So what I'm showing here at the bottom is, as an example, the life cycle of the sun. And you see over on the left, you have the birth of the sun. And then you see how the sun being a moderately sized star, looks almost the same when it's 1, 2, 3, 4, 5, 6, 7, 8 billion years. Until around 9 billion years, it starts running out of fuel. It starts running out of hydrogen in its core. And it becomes a red giant, and eventually the red giant becomes a white dwarf. It starts cooling off. Okay. That's the example of the sun. But, of course, you know that the smaller stars do this for much longer, whereas the big stars go through this process much faster. And so when you plot, as I do up here, the stars in the star cluster, if you plot their color, okay, as a function of their brightness, you will see that you have the small stars down here that are cool and thus red, and then you go up to more and more massive stars until you get up to these very hot blue massive stars. Okay? So to help you with the visuals, here you have the smart cars and the Corollas and the Humvee limos, right? And so because all of these stars in the star cluster have the same age, right? At that particular age, what you'll see is that the more massive stars have already become red giants. They've already used their fuel and are on, they're just coasting along in neutral, right? Whereas the Corollas are still driving and the smart cars are still driving. And so what happens is that these hot stars, they start evolving over and becoming red giants. We call that particular place in this color brightness diagram the turnoff point. And so now we can take, when we have this very, very characteristic pattern in this diagram of a star cluster, you can take your theoretical models and you can start saying, okay, I have a model here for an age of 2 billion years. And I plot that on top and I say, that doesn't really fit my observations of the colors and brightnesses of these stars. Okay, well, I'll try a slightly older model for how the colors and the brightnesses should look of all these different stars. Not really good. You take a third model with a slightly older age, and bingo, right? It's right on top. So again, you have a model of how the colors and brightnesses of stars at a given age should be depending on their mass. And you can plot that. And now, with one strike, you've determined the age of all of these stars in this cluster, in this star cluster. And that is a very, very powerful thing. So that is why we can determine the ages of stars in star clusters really well, because these models of stellar evolution, as I said, have become really good by now. Now, you might have noticed that all this is all fine and good, but within this yellow box here, there was no real difference between the three different models, whether it was 2 and 3 and 4 billion years, right? These Corollas and smart cars down there, they haven't really changed, right? The solar type stars and the low mass stars, they're going through their life and they're not really changing much. They're not changing their color or their brightness. So down in that region, it would be very difficult to distinguish whether, if you're just looking at a single star, like the sun, you can't tell if you plot your models on top of that. You have no way of telling whether this star is 2 or 3 or 4 billion years old, right? And that is a real problem, right? Because, as I told you, the stars down here, these low mass stars, are by far the most numerous stars out there. Okay? They're dominant in our solar neighborhood. Most of them, we find planets around them. This is the real problem we're faced with. We simply cannot determine their ages to any reasonable precision or accuracy. It all comes down to this, of course, right? As I pointed out, for the vast majority of the lifetime of a star like the sun. Oops, I'm going backwards. Should stop using this thing. For the vast majority of its lifetime, this star looks almost the same. And so to just drive this home one more time, let's imagine that the same was true for humans. Okay? Let's imagine that humans operated like that. Listen, we were born as babies, but on our first birthday, 1 year along, we looked like an adult. And we looked like an adult through our 20s and 40s and 60s and 80s until suddenly when we turned 100, we started looking old. If that was the case, you couldn't just walk down the street and look at someone and say, oh, you know, I think she's in her 20s, or I think he's in his 50s. You would actually have to go up to them and saying, hey, sir, can I see your birth certificate? That was the only way you could find out, right? And that's the problem we have at stars. So what we're faced with the challenge of finding something about these solar type and lower mass stars, something that changes not just when they die or when they're born, but all the time, something we can observe, something that changes steadily throughout their lifetime. And there is one such property, and I have alluded to it already in my examples prior in this talk. Stars spin, and when they're young, just like a top on a table, they spin fast, and as they get older, they spin more and more slowly. So, the spin rate of a star can be used as a clock to determine its age. We have not yet built this clock, okay? We're putting it together. We went to Home Depot and we bought the wood and the nails and the pulleys and the cogwheels and all this stuff. We're trying to build it, and we're trying to build this relationship between rotation and age. And the term for that is, we call that gyrochronology, right? From something spinning and determining the age of it. Now, how do we determine the rotation period of a star? As you can see, all the stars I'm showing you have spots, just like the sun has spots. But when stars are younger, they have bigger spots. So what you're looking at here is a little bit younger star. And so what we do is we measure the brightness of a star repeatedly, frequently, continuously. And when the spots comes across the face of a star, you can see the brightness goes down. And when the spots go on the backside of a star, the brightness goes up. And so as the star spins and these spots on the surface of the star comes across the face and they go back on the backside, you see that the brightness oscillates up and down. And when we have measured the brightness of a star repeatedly over an amount of time, and we're satisfied with our result, we can then examine this light curve, as we call it, for the star. And we can look for patterns that repeat themselves, right? And that gives us the rotation period of a star. And that can actually be done very, 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 very precisely, depending on the quality of your data. So we have something we can measure very precisely, and something that changes gradually with the age of a star. Now, this is a good start, right? Of course, there is no endeavor without challenges. As stars grow older, they start spinning slower, and they have fewer and fewer spots, and the spots become smaller and smaller. We think we understand why this is happening, but nonetheless, we're faced with this challenge. So as you can see over on the left, you have a very young star with huge spots on it, spinning very quickly. And in the diagram below, what I'm showing is that the brightness fluctuations are large and very frequent. So in that case, it's a piece of cake. We can do that, okay? In the middle, you see a moderately aged star. It has now smaller spots and is rotating more slowly. So the brightness fluctuations become smaller and less frequent. We can still deal with that, but it becomes more challenging. But when the star gets as old as the sun, or older, they have tiny spots, and they rotate very slowly. And so, as I'm trying to illustrate here, the brightness fluctuations becomes almost not visible, considering that you always have noise in your data. So they become very challenging, and they're very long duration. So it becomes really challenging to measure the spin period of an old star. And of course, we want to do that, because how else can we build our clock? it's no good to have a clock that can only tell you the time between noon and 3, right? You would kind of like it to be able to tell the clock throughout the whole day. The same with the stars. If we have to build a good clock, we have to be able to calibrate it for old stars as well. And that is where, well, let me first show you. So what we're trying to do, just to drive it home with a picture, is to establish this relationship, right, between age and spin period. And what we have at the present time is we have these young, fast rotators down here with big spots. The reason we have the ages for these stars is because they're actually in star clusters. Remember I told you how we can determine the ages of star clusters well? So we use stars in star clusters on purpose because we know the ages really well. And then we have one star out there. I'm sure you can guess which one it is, right? It's the only star beyond 500 million years. Beyond 5 million years, it's the only star for which we know its age well and its spin period well. So that is the challenge, right? We don't know what's going on in there. And so this whole scenario that I built for you here with the gyrochronology, with the building a relationship between the age and the spin period, was sort of the driver behind, one of the drivers behind the Kepler cluster study, which I'm leading, which of course, as you can see in the name, has to do with Kepler, right? So Kepler has the capability, in addition to being this fantastic planet-finding machine, the way it finds planets is by measuring the brightnesses of stars extremely precisely, at unprecedented precision. Continuously, every half an hour, we get a measurement of the brightness of a star, right? So, bing, right? This would be a good instrument to use to determine the spin period of old stars, where the fluctuations are extremely small and of long duration. What you want there is something that can measure the brightness of a star really precisely, okay, and continuously. And what happened in the animation while I was talking about that, and maybe you weren't listening, because what you saw is that Kepler was launched, of course, not to orbit the Earth, but to orbit the sun, okay? And what it's doing is doing that so it can stare at the same part of the sky all the time, uninterrupted by the daily cycles of day and night. And the place it's looking is a place near the constellation of Cygnus. That's shown by this mosaic of squares up there. And it's looking at about 160,000 stars, okay? Continuously, all the time. Every half an hour we get a measurement, okay? And so what we're doing with Kepler is we're trying to fix this problem, okay? And the first thing we have done successfully with the Kepler cluster study is to measure the spin periods of stars now that are in a cluster that is 1 billion years old. So we have taken a first significant step toward filling in this gap, toward building this clock that will allow us to determine ages of stars based on their rotation. The next one we're working on at the moment is a 2.5 billion year old cluster, right? So you can see we're going to get a very important data point out there, a very important data point in establishing this relationship between age and rotation. And there's even a 9 billion year old cluster within the field of view of where Kepler is looking that will allow us to take this relationship beyond the age of the sun. And of course, again, the idea is that once we establish this relationship, right? Once we have this relationship, however it's going to look, we can then turn around. We can address a whole range of astrophysical problems, but in the context of Kepler and extrasolar planets, we can turn around, we can measure the spin period of one of these stars for which the planets are orbiting, and we can determine its age. And when we have the star's age, we have the ages of the planets and the planetary system. And so I'll end there, putting up this brief summary of what I think you should take away from this, right? That knowing stellar ages is fundamental to understanding the evolution of astrophysical phenomena. Determining the ages of the most numerous stars, stars like the sun or smaller, is particularly difficult. But the technique of gyrochronology, the study of the relationship between the stellar age and the rotation, is a promising new technique. And so I'll stop there and take any questions you might have. Thank you.